Welcome everyone. This is my Physics 58E term project presentation. It will be about antiferromagnetic spintronics. I hope you enjoy it and I hope you can learn things about the topic and will be beneficial. So this is the outline I prepared for the course. I had to mention a little bit about all the sub-subjects since the antiferromagnetic spintronics is a deep topic. So I will start with a little discussion about the history of antiferromagnets. Why do we call them antiferromagnets and who has worked for antiferromagnets? What is the pioneers of antiferromagnets? And after that, I will talk about observation techniques of antiferromagnetic structure. How do we observe it? What are the techniques we most commonly use? And at the third part, I will talk a little bit about the susceptibility of antiferromagnets because it's quite important to know the susceptibility susceptibility calculations of the antiferromagnets in order to use it in the magnetic devices. At this section, I will just have a few words about the quantum mechanical approach only to explain why antiferromagnets are too exotic and it's hard to understand even in the quantum mechanical point of view. And at the E, before passing to the spintronic of the antiferromagnetic materials, we need to learn how to manipulate the magnetic moments of the antiferromagnets by exchange fields, by magnetic fields, by optical manipulation. And at the end of the subsection, I'll show a few pictures about magnetic textures occurring on the surface of the antiferromagnets. At the second part, I will briefly introduce very few and very important studies about usage of antiferromagnets in spintronic systems and the most important, most fundamental components of the spintronics, which is spin transfer electronics, spin orbitronics, and at the end, I will have a few words about spin caloritronics. So I will start with the introduction parts. And as you can see here, the difference between the antiferromagnets and the other magnets are on the picture. So we can basically say below the Néel temperature, spins are aligned anti-parallel in the magnetic domains, unlike the ferromagnetic structure, which is parallel. And unlike ferromagnetic structure, the spins are equal, have equal magnetic moments. And unlike paramagnetic structure, there is a there isn't a random distribution of the magnetic spins. Okay, so here's another comparison of the time temperature dependence or susceptibility of three different magnetic materials. First one is a paramagnet, second one is a ferromagnet, and third one is an antiferromagnet. This scheme is important. It's quite it seems quite alone right now. It's just the figure with three graphs, but at the end of the lecture, we will understand how important it is and how differs it is depending on the very fundamental structure of the antiferromagnetic moments inside material. So these two people is Louis Néel and Lev Landau, who are the pioneer of the antiferromagnetic technology because they have investigated the antiferromagnets in the most basic sense. To make a short comments on their studies, I took some notes. And when regarding the Néel studies, he basically tried to obtain a mixture of Heisenberg's exchange energy phenomena and Weiss molecular field concept. Worked on magnesium, chromium, iron cobalt, iron chromium alloys, and iron chloride, chromium chloride, nickel chloride salts, and temperature dependence of their susceptibilities. When he combined two theories, mentioned the possibility of having two opposite magnetic moment layers in the same material. He also introduced the term local molecular field, obtained the anomalous temperature independence of susceptibility of platinum cobalt. The peak of susceptibility temperature graph on antiferromagnets named after him, what we call the Néel temperature. When we talk about the Landau studies, he worked on anhydrous crystals of chlorides of iron, cobalt, nickel, and chromium, obtaining the fact that the paramagnetic domain susceptibility is inversely proportional to temperature, but in a faster fashion than ferromagnets. This part is important, without observing a ferromagnetic behavior when the sample cooled down below the Curie temperature, offer the magnetic structure of layered system with a strong dependence on exchange field. And apart from Nel, he also focused on the effect of interactions between magnetic moments and lattice and magnetic impurities, which represents the magnetic anisotropy of the system. And this is a graph of data which gives us the paper per year value depending on the years, starting from the 1940s, which means that, which explains how big opportunity that Nel and Landau gave us on the research of antiferromagnets, and they open a huge gate for us to dig deeper. And now I will talk about the observation techniques of antiferromagnets. First one is quite similar one from the previous talk, and we can understand our material has an antiferromagnetic structure by obtaining the exchange bias, by cooling the material, cooling the bilayer under the Nel temperature. If we have the exchange bias field in the hysteresis loop, then we understand that our bilayer is an antiferromagnet on top of a ferromagnet. And the most fundamental way to understand the antiferromagnetic structure is neutron scattering. The scheme you see on the screen is basic Bragg law. As we already know, the Bragg law is based upon the scattering of X-rays. But here, we used neutrons instead of X-rays. The reason behind this is we try to obtain the magnetic structure. So we are after a magnetic scattering of waves. We want waves to be scattered magnetically, so we don't want any electrical charge on the waves. So instead of using X-rays, which are scattered by the electron density, we use neutrons, which have no electrical charge, but a magnetic moment, which means that can only be scattered by the magnetic moment of the nodes on the planes. So as you can see in the two different pictures, there are two different planes. One is a basic plane, and in the other one is there's a third additional plane, which has another node in between two others. So what does this mean for our magnetic structure? So we are after a structure of two spin bilayers. So we need to find a planar organization similar to the second picture. And here we need to first I need to talk about this. So imagine that the first and the third layers of nodes have the same property, but the second node has the opposite property. That means that scattering will be inverse. So we will have another peak value, another intensity peak, another value of the intensity on our calculation, on our measurements. So how do we run this experiment? There's a research reactor where the neutron beam is being accelerated and directed to the material. And as you can see, the atoms inside the crystalline sample. And when the neutrons collide with the atoms in the sample material, they change direction, which they are actually scattered by the magnetic moments. They are elastically scattered. And after the scattering, their intensities are being measured. So you can see two different cubes, which are actually the same material. One is the magnesium oxide before being magnetized, and the other one is magnesium oxide after being magnetized. Being magnetized, I meant that we only bring temperature under the Nel temperature. So we observe the unit cell is changing because there are two different spin behaviors on the material. We observe not the same spin structure, but two different spin structures which change the unit cell structure. And this is the outcome of the neutron diffraction experiment. This is 80 Kelvin and 300 Kelvin measurements for the neutron diffraction experiment for the magnesium oxide. As you can see there, under the Nel temperature, 111 and 311 is the two individual peaks coming after the material. But when we bring it to the around the room temperature, we can observe only one peak, which means that in the room temperature, there's only one scattering mechanism occurs. But when we bring it under the Néel temperature, there are two different lattice sites and two different featured spin states, which is one is up and one is down, which have antiferromagnetic structure, and they're scattering two different directions. So I have two different direction peaks in the measurement. Okay, we just talked about how X-rays are not so useful for antiferromagnetic detection, but here, vice versa, I will talk about how can we use X-rays for understanding the antiferromagnetic nature. So this one is called X-ray magnetic linear decolorism. They're being used as searchlight effect, which is caused by the spin-orbit coupling in antiferromagnets. As you can see in the picture, spin-orbit coupling distorts the charge and creates a polarization dependence. As I mentioned before, X-rays are scattered into electron density, but electron density is isotropic, so you cannot understand the direction or axis of a system by its scattering. So in order to couple the spins with the orbits, there's a linear polarization of X-rays and sending into the material to understand what is the axis of the and the anisotropy of the antiferromagnetic material. So depending on the intensity, we can understand if my antiferromagnetic spins are aligned like this, or this, or this, in which perpendicular axis we have. So I will say a few words about susceptibility of antiferromagnets, since it's quite important. And this is the Weiss theory of antiferromagnets. And Weiss offered a theory for as the magnetic field inside the material is sum of the two different components. And one is HM, depending on the molecular field, he assumed. And he calculated the value of the susceptibility as it's, you can see it in the picture. So what is the difference on antiferromagnets? So in antiferromagnets, we need to have two different spin layers with opposite directions. So if my magnetization one, if my magnetic moment one is like this, it must be the opposite of the other spin layer. So in order to understand the spin correlation, we can name them as MA and write it like this, and vice versa, we can write MB like this. The trick is I have two spin sublattices A and B, and only the interaction between the A and the B lattice is important rather than AA and BB interaction. This is the most important point in the antiferromagnetic susceptibility calculation. So when we want to understand the total magnetization, we need to extract them because they are looking at the different direction. But when we want to explain the change in the magnetizations of the system, and we need to add the changes in the structure. So if you look at the total magnetization, this is the term, and the susceptibility can be written like this. And we can see here that the theta term, unlike the ferromagnetic system, the theta term is written as plus instead of minus. So if we want to calculate the susceptibility at the Néel temperature without an external magnetic field, we can assume that the only field affecting on a magnetic moment is, for example, at the B, it's the molecular field constant times minus times MA and vice versa. And when we insert the variables, we can see that the theta term equals to Néel temperature. And the first graph represents the spontaneous magnetization, which is coming towards to 0 at the Néel temperature, because after Néel temperature, it's turning into a paramagnet and loses its spontaneous magnetization. And the problem about the magnetization and its dependence on the external field, there is a anisotropy fact, because if my antiferromagnetic spins are aligned like this, is parallel to the external field. But if they're aligned like this, it's directly perpendicular to the external field. So what happens next? This is the calculation what's meant to be to calculate the susceptibility when the field is parallel to the magnetic moments. And here, alpha constant is described mh over kBt, and the alpha term is directly proportional to the h. So the dependence on h, derivative of h, also the derivative of alpha. So the term is written like this. At the end of the calculations, some huge amount of calculations, the dependence of alpha on NML term is plotted like this. And this is the susceptibility term when the external field is parallel to the antiferromagnetic layer. And the important part is it has T over the component. So it is T dependent. But when we convert it to the perpendicular side, we observe that it's not the same thing. By doing the calculations, spins are canting in this way, and we observe that, we calculate that the perpendicular susceptibility is temperature independent. It only depends on the molecular field constant. And this term is the susceptibility of a powdered material, which means that if we have a polycrystal, which includes both perpendicular spins and parallel spins, this is the way we calculate the susceptibility of it. And this is the total picture of how susceptibility of the material changes depending on the anisotropy of coming external field and temperature. So I will have a few words about the quantum mechanical approach. So this is the basic mechanism of magnesium oxide that we have talked about before, about the neutron scattering section. So as you can see here, at the first picture, the orbitals are standing like this, and the last orbital of the magnesium plus 2 ion, is open, and it's sharing an electron with the O minus 2. It's the same. So depending on the Hans rule, if we have an upspin here, we can only collect the downspin here. So this creates an antiferromagnetic structure, just like in here. So if we have magnesium 3, this one slot will be open, will be fully empty, and it will share also this upspin, and this one will share this upspin. So in oxide orbitals, there will be an antiferromagnetic system created. So as we say the quantum mechanics, we need to talk about a Hamiltonian. So what is the point of antiferromagnetic systems are so too complicated? This is how we write an Hamiltonian for a spin chain, which the J is an exchange energy integral, and those are the spin operators of each neighbor spin. So when we look at the ground state of a ferromagnetic spin chain, we can easily say all up spins or all down spins, which is J is greater than 0. But when we look at an antiferromagnetic spin chain, we just cannot say directly that all spins are up, down, or in other order. We have a different complex wave function to describe the ground state, which makes it quite complex near ferromagnetic systems. And this is the types of the antiferromagnetic orders. At first picture, you see an ferromagnet. It's all spins are directed in the same way, they are parallel. So in the A type, it looks this way. At the C type, it looks, and it has another geometry with the dependence of the anisotropy. And the G type, it has a different cross-sectional geometry. And this is how spatial of the antiferromagnetic spins looks like. And at the K vector and the This is a representation of the antiferromagnetic spins. So the manipulation of magnetic moments of AFMs. As we talked about before, exchange bias is quite good. Is a quite good way to understand the AFM nature, and it's also a way to decide the interfacial moments of the AFM, since in order to manipulating ferromagnetic moments, since we can do it with an external field easily, we can also describe the layer just at the interface of the antiferromagnet, and what spin anisotropy, what axis can it have, by using the cooling field and its direction changes. This is by changing the field cooling direction, it's possible to dictate the designated direction for spin order. And this is the external manipulation of AFM magnetic structure. So this is Stoner-Wolfach model. This is important. I don't want to bore you with numbers and equations, but this is important to understand in order to what is happening between the antiferromagnetic spins and antiferromagnetic external magnetic field applied, and what is the role of the anisotropy. The phi is angle between the magnetic moment and the external fields. JAF is the antiferromagnetic exchange energy, and magnetization of one sublattice is represented at MS. K is the energy density of one sublattice with uniaxial anisotropy, and H is the applied magnetic field. So when we assume that we have perpendicular case, we need to apply an external field that is perpendicular to the spin order. Spins are canted. Canted means like this. Canted until the saturation have been achieved when the Zeeman energy, which is caused on the spin by the external field, is equal to exchange energy, which is the the energy between two antiferromagnetic spins, and the spin flow field. So when the anisotropy is weak compared to exchange energy, which means that the anisotropy energy is small when we consider it with the exchange energy between two antiferromagnetic spins, no net magnetization until the external magnetic field compensates the anisotropy. The spin flow field occurs. In case of anisotropy is large compared to exchange energy, net magnetization jumps directly from 0 to saturation value, which is called spin flip. In this graph, it's easily can be seen. As you can see, there's some spin flip and spin flow fields for antiferromagnets, and this is the field applied perpendicularly. And the spin flip fields for some materials are given below. For magnesium MnF2, it's 9 to 10 Tesla. For this compound, I can pronounce it, it's 1 Tesla. And it's below 2.6 Tesla. For iron phosphor, it's 42 Tesla. This means that to flip this magnetic moment, you need to apply 42 Tesla, which is quite absurd number. Another way to manipulate the magnetic moments of the antiferromagnet is optical manipulation, given by the magnetic impulse by using the laser pulse. We are talking about the pulse. It's magnetization dependent pulse, and just like this, it's like a passing by a potential well and giving the inertial motion as much as possible. There have been a study about this by Kimmel et al. And the figure presents the theoretical study is given below. You can see here the spin switching technique by applying H by an optical pulse. And magnetic textures in AFMs also can be observed, which is in the picture, at the first one, black and white one, we observe, we see a Monte Carlo simulation. It's a simulated spins, as you see the directions. And the second one is simulated from STM data. And the third one is directly STM data, experimental data. So we can observe magnetic textures in AFMs too. It's a computed skyrmion in a G-type checkerboard texture antiferromagnet. Its top view and cross-section of the antiferromagnetic structure. So now I will talk about the most important topics of antiferromagnetic spintronics, starting with spin transfer electronics. So first component should be spin transfer torque. At the left, you see torque exerted on a ferromagnetic system when a spin current Js is injected. And in the right, you see torque exerted on an antiferromagnetic system when a spin current Js is injected. Torque must be sum of two different sublattice components. P represents the symmetry of the system, such as polarization of spin in spin waves. So there must be a polarization in the system to apply the torque on each individual spin lattice. Okay, so this is a brief discussion about how a spin transfer torque or applied external magnetic field or staggered field applies into two distinct antiferromagnetic spins. So at first, you see H as the applied magnetic field, and TE means that the torque being applied to each magnetic moment by themselves, by each other. And the TH is the torque applied by the magnetic field, applied magnetic field on each magnetic spin, which they do not compensate. They compensate each other and they do not make spins can't move. So it is unlikely to move spins when even if you don't have the required magnetic field, which is a lot in very much of the antiferromagnets. At the second one, there's a staggered field, which means that two different applied magnetic fields for each magnetic moment, and the same exchange components, torque components are present again. And as you can see here, two staggered magnetic fields applied to the system, and the torque is applied in this direction to the spinning plane direction to the spins, and the torque is actually canting the spins. And when we apply spin transfer torque to the system, the spin transfer also cants the spins. So we can say that it is a way to cant spins and manipulate the spins. By the way, P is for the polarization of the spin. There must be a polarized spin current. So this is a quite important stability diagram of a ferromagnetic and antiferromagnetic bilayer. We are assuming that a polarized spin current getting into an antiferromagnetic structure with up spin here is given by the pink one, and the antiferromagnetic moments are given by purple one. So J is the critical current, and HSF is the H spin flop, means that the required external field to obtain spin flop. So ferromagnetic order parameter and spin flop critical current. So as you can see here, at the amount of critical current, about a certain order of critical current, the antiferromagnetic moments spin. And it's the same on the side that in two ways of critical current and applied external field, which is bigger than spin flop field, which means that there's only a specific domain between those values on the system, which this antiferromagnetic domains remain in a stable state. And it's also possible to obtain movement of the magnetic structures by using spin transfer torque. And unlike the ferromagnets, antiferromagnetic structures can be moved without the Magnus force due to their unique antiferromagnetic dynamics. And about spin pumping, it's also possible to achieve the spin pumping with antiferromagnets. Terahertz radiation pumps the spin currents into adjacent metals, which get converted into charge currents and concomitant charge voltages through the spin Hall effects. And they also trigger each other. So it's also possible to obtain spin pumping by antiferromagnets. One important topic is spin transfer electronics, spin mixing conductance, and penetration depth. I needed to make comments and describe the terms in this one. Interfacial spin mixing conductance. This mechanism works to determine the spin's reorientation upon the reflection at the magnetic interface. And spin penetration depth means how far can spins propagate inside the material while retaining their spin alignment. And in the spintronic devices, to protect it from a spin information loss, we first need to know what kind of losses we have. So we have spin flip relaxation, which means that it relaxes the angular momentum through the lattice by spin orbit coupling and magnetic impurities. And spin dephasing, it relaxes the component of the spin density that is transverse to magnetic order parameter. This is an important study about this. Spin polarization upon electrical injection, which gives us the three different scenarios. One is for applying an electrical injection into a ferromagnet, and at the B, it's a G-type ferromagnet, G-type antiferromagnet, and at the C, it's an L-type ferromagnet. So as you can see the differences, here it's directly polarized, here it fluctuates, and here it's directly zero component. So this is a quite good example for the spin penetration depth and spin mixing conductance properties of antiferromagnets. And here it is also quite important study for the spin mixing spin depth. So here at the spin injector, the magnetization is a spin current is supplied by a spin pumping, and then by using the chromium as the spin conductor to disable the interfacial effects between the antiferromagnetic layer and ferromagnetic layer. When it comes to inserting the spin current into the antiferromagnetic layer, it is being observed that there is a current and there is a potential difference, which is important to understand the thickness dependence of the iron manganese to analyze the spin penetration depth, how far spin can go inside the system. And this is the dependence of the antiferromagnetic layers, which are two different layers have been used, iron manganese and iridium manganese, and the spin penetration depth given here is Frango et al. And this is a quite important data from Bals et al. And some of the antiferromagnetic metals and their spin penetration depths depending on the bulk resistivity. And a few words about spin orbitronics. Most important phenomenon in spin orbitronics is anisotropy magnetoresistance. First found in 3D transitions metals by Kelvin. It's 19th century. Orientation of the magnetization of materials with respect to direction of electrical current is caused by the anisotropy of the electronic structure induced by spin orbit torque. And AMR is invariant under magnetization reversal. Non-crystalline AMR arises from the deviation of current direction with respect to magnetization. And crystalline AMR depends on crystalline symmetries. And as we can see, there are two distinct parts of AMR, which is one depending on the crystal structure, and the other one does not depend on the crystal structure. So there's an important study that I also presented it before about the iron rhodium. It is shown that basically an antiferromagnet can be used as a memory device, as a signal, as a memory device in the room temperature because of the unique properties of the iron rhodium, which makes it phase transition into ferromagnet to the antiferromagnet. And two important components of the spin orbit torques are the spin Galvanic effect and the spin Hall effect. The spin Hall effect is caused by the spin orbit coupling, and spin Galvanic effect is caused by the inversion symmetry, lack of inversion symmetry in the material. And this study is quite important for the spin Hall effect, which is the proof of the antiferromagnetic metal iridium manganese is as efficient as a heavy metal, which has high spin orbit coupling, platinum, when it comes to achieve achieve this potential, which is caused by the inverse spin Hall effect, by two different spin current injection methods. One is the spin pumping, and other one is the spin Seebeck effect. As you can see here by the study, I mean, if you want, you can read the whole study as well. But at the end of the study, it's seen that iridium manganese is also as efficient as the platinum as a layer to be used on the spin Hall effect studies. And this is a quite important one, the spin Orbitronics inverse galvanic effect. In this study, current-induced switching has performed. And this one is important because it is a actual application produced. And I want to show a little video about this. I think my time will be okay.
So there are hackers in the room, right? So we managed to apply electrical currents and manipulate antiferromagnets, and the wonder of it is that we did just at room temperature with 5 volts, almost like a battery. You could do it, and actually.
Oops, sorry. It was here.
Proud. Especially, I've never seen something like this. If you
this is how the structure of the study works.
My hosting institution at the moment, going from papers to something USB that it's featuring the
which makes the antiferromagnetic materials current switching possible. And at the end, the spin caloritronics is a field that achieving the spin spin current by the change in the temperature, which is a temperature gradient, and makes it injects these electrons by spin and inverse spin Hall effect. So this was all about it. Thank you. I hope you learned something from the presentation.